Welcome to the Deep Dive. Today, we're digging into something pretty fundamental that's happening in AI. A shift beyond the kind of AI we mostly see today towards systems that are, well, more flexible and, really importantly, systems we can actually understand. It feels like a really pivotal moment.
It really is.
And, it's funny how the term AI itself has changed. I remember not too long ago, researchers almost avoided it. They preferred machine learning, maybe deep learning.
Absolutely, yeah.
But now,
Yeah.
it's everywhere, which is great, but it can also make it a bit fuzzy, what we're actually talking about.
That's a really good point. And, to try and cut through some of that fog, IBM actually came up with a pretty helpful way to think about different levels or types of AI. So first, there's what we mostly have now, which they call narrow AI. These are the systems, that are amazing at very specific things, recognizing pictures, translating languages, playing complex games like Go.
Right, the specialist systems.
Exactly. Super powerful within their lane, but that lane is, well, narrow. They have built-in limits. Then, way out on the horizon, there's general AI. That's more the sci-fi idea, right? The truly autonomous machine intelligence that can do anything a human can, maybe even decide its own goals.
The stuff that gets the headlines, sometimes worryingly.
Yeah, precisely. And when you ask researchers when we might get there, you usually hear something like 2050 and beyond.
Which basically means we don't really know.
Pretty much. It's decades away, if ever, in that form. But the really interesting part, the bit we're actively working towards now, is the middle ground. That's what IBM calls broad AI.
Broad AI. Okay, so what does that look like?
So this isn't science fiction. It's about building systems that can handle multiple tasks, work across different domains, take knowledge from one area and apply it somewhere else. They need to fuse all kinds of data, text, images, sensor reading, structured stuff, messy, unstructured stuff. They need to work everywhere, from massive cloud servers down to tiny devices on the edge. And this is the crucial bit for broad AI. These systems have to be explainable. We need to know why they make decisions. They need to be secure, fair, and critically, they need to work without needing mountains of data. They have to be efficient with small data.
Those sound like the big hurdles. Explainable, fair, small data.
They really are. Those are the major challenges we're tackling to get from narrow to broad AI.
Okay, that framework, narrow, broad, general, that's super helpful context. Which leads to the obvious question. If narrow AI is so good at its specific jobs, why can't we just, make it bigger? What are those specific limits holding it back from becoming broad AI?
That is exactly the core question. And one of the most promising answers, a key method for bridging that gap, is something called neuro-symbolic computing.
Neuro-symbolic, okay.
Yeah. It's essentially about bringing together two really powerful, long-standing traditions in AI in a principled way. You take the amazing learning ability of neural networks.
The deep learning stuff we hear so much about.
Right, and you combine it with the logic, the reasoning, the kind of knowledge representation that symbolic AI has always focused on.
Okay, so you're saying deep learning, despite its successes, we see it generating art, captioning photos, beating world champions, it has fundamental weaknesses. Cracks in the foundation, you might say.
That's a good way to put it. The achievements are spectacular, no doubt.
Yeah.
But yes, underneath, there are some pretty significant limitations. One of the biggest is what we call brittleness.
Brittleness.
Yeah. Deep learning systems are essentially incredibly sophisticated pattern matchers. They get really good at recognizing patterns they saw over and over in their training data.
Okay.
But they often don't develop a real conceptual understanding of what those patterns mean.
Can you give an example?
Sure. There's a famous one involving Art Merritt Oppenheim's sculpture, the teacup covered in fur.
Oh, I think I know that one. Weird piece.
Definitely memorable. So you show an image of this furry teacup to a top-of-the-line image recognition system, and often it'll confidently label it teddy bear.
A teddy bear, what?
Well, think about it from the system's perspective. It sees something roundish, soft-looking, furry. What does it know that fits that pattern? Teddy bears it's seen in its training data.
Ah, okay.
It doesn't understand the concept of a teacup and the separate concept of fur as a material, and then reason that they've been combined in an unusual way. It just matches the surface features. And because this specific combination is weird, it's out of sample, it falls back on the closest pattern it knows.
So it fails on edge cases, basically.
Exactly, or things just slightly outside its experience. We see this in image captioning, too. Systems might describe a photo of an airplane on a runway as a man riding a motorcycle on the beach.
That's not even close.
Right. The words might sound vaguely plausible together, but it shows a complete lack of understanding of the actual scene. It's just stringing together statistically likely labels based on pixels, not comprehending context.
Okay, so it's matching pixels, not meaning. And you mentioned training data that seems key. Their success feels tied to having huge amounts of data, doesn't it? Is that another limit?
Absolutely. That's the second major point. The deep learning revolution, sort of post-2012, was really fueled by two things happening together. One, huge advances in computing power, especially using GPUs.
Right, the graphics cards.
Yeah. And two, the availability of massive labeled data sets. ImageNet is the classic example where millions of images, all carefully categorized by humans.
So they need that scale.
They're incredibly data hungry. Often you need thousands, even millions of examples for a deep learning model to learn a task well.
Which is totally different from how people learn.
Totally different. Think about it. I can show you just one example of something you've never seen before, like that fur-covered teacup again, maybe with its saucer and spoon.
Okay.
You get it instantly, you understand its properties, and then you can reason about it in new ways. Like, if I showed you a broken one, you'd know it's still fundamentally the same object, just damaged. You could answer weird questions about it.
A deep learning model couldn't do that from one example.
Not even close. It needs that massive repetition. And this leads directly to the small data problem.
Ah, because most real-world situations don't have millions of perfectly labeled pictures.
Exactly. Think about applying AI in, say, diagnosing rare diseases or predicting failures in specialized industrial equipment or even complex financial modeling. You just don't have ImageNet-sized data sets for those specific problems.
So if AI needs big data, it can't work on small data problems.
It struggles immensely, and even the big data sets like ImageNet have hidden biases. Researchers at the MIT IBM lab did this interesting experiment. They took objects and put them in weird places like a hammer on a bed, a knife in a bathroom sink.
Things you don't normally see.
Right. Humans could still identify the objects with over 95% accuracy, but the best deep learning systems, their accuracy crashed down to like 40–45%.
Wow, that's a huge drop, just from context.
Just from putting familiar objects in slightly unfamiliar settings, it really shows how much they rely on the specific statistical patterns they were trained on, how brittle they are outside that distribution.
That fragility is striking. And I've also heard about AI systems being, well, fooled, vulnerable to attacks. Right. Is that related to this brittleness?
It absolutely is. That's another really concerning limitation, their vulnerability to adversarial attacks.
How does that work?
So someone can make tiny changes to an image's pixels, changes that are completely invisible to a human eye, but they can cause the AI to make a wildly wrong classification.
Like what?
There are examples where a picture of a stop sign after these tiny pixel tweaks is confidently identified by the AI as, get this, a brown teddy bear lying on top of the bed.
Seriously, that's bizarre.
It is, and it's not just digital tricks. Researchers have created physical things, like special t-shirts with weird patterns printed on them. If someone wears that shirt, they can become effectively invisible to AI systems designed to detect people. The person is right there, clear as day to us. Maybe the shirt looks a bit odd, but the AI just doesn't see them, even if the shirt is folded or wrinkled.
That seems fundamentally weird about how they perceive the world compared to us.
It really does. There's something different going on, and the security implications, obviously, are pretty significant.
No kidding. Okay, so they're brittle, they're data hungry, they're easily fooled. What about transparency? Can we understand why they make a certain decision?
That hits on another huge barrier, the lack of explainability. Deep learning models are often described as black boxes.
Heard that term a lot.
Yeah. And it means it's incredibly difficult, sometimes impossible, to trace back why the model produced a specific output. Why did it approve this loan but deny that one? Why did it flag this image but not that one?
And that's a problem for?
For everything. For trust. How can you rely on a system if you don't know how it works? For debugging, if it makes a mistake, how do you fix it if you can't see the error in its logic? For deployment in sensitive areas like healthcare or finance, where regulations often require you to be able to explain decisions, it's a massive roadblock.
Okay. And one more, you mentioned reasoning earlier.
Yeah.
How do they fare with actual logic?
That's probably the biggest gap for truly broad AI. They struggle profoundly with reasoning, especially compositional reasoning, understanding how parts relate to form a whole, or answering questions that require multiple logical steps.
Right.
Imagine a picture with different colored blocks stacked up. You could ask a child, how many blocks are to the right of the tall blue one? Or, What shape is the block sitting on top of the red cube?
Yeah, a kid could figure that out.
Right. But pure deep learning systems find these kinds of questions incredibly difficult. They might recognize block and blue and red, but understanding the spatial relationships right of, on top of, and combining those concepts to answer a multi-step question that requires a kind of logical framework they just don't have internally. They lack that explicit grasp of relationships, cause and effect.
So, okay, we've got brittleness, data hunger, vulnerability, black box explanations, and poor reasoning. That's quite a list of limitations for deep learning on its own.
It is, and that's why just trying to scale up current deep learning likely won't get us to that vision of broad AI. We need something more.
Which brings us back to neuro-symbolic computing. You said it combines deep learning with symbolic AI, the good old-fashioned AI.
Exactly. It sounds almost counterintuitive looking back to AI's roots, but there's a really powerful idea here. We have to go back briefly to the very beginning, that 1956 Dartmouth workshop where the term artificial intelligence was actually born.
Okay.
Right from the start, there were kind of two main schools of thought, two venerable traditions, you could say.
What are they?
On one hand, you had the precursors to neural networks. The idea was inspired by the brain, focusing on learning complex patterns from data, adjusting connections weights between simple processing units. For a neural net, an apple is defined by how it looks, right? The pattern of pixels that statistically correlates with the label apple.
Got it. Learning from examples.
Yep. And on the other hand, you had symbolic AI, sometimes called Jew FAI, good old-fashioned AI. This approach was totally different. It was about representing knowledge explicitly, using symbols and logical rules.
So how would symbolic AI see an apple?
For symbolic AI, an apple is something specific. It's a type. Fruit, it grows in. Apple tree, it has parts. Stem, body, its body has shape. Roundish, hey, typical color. Red or green or yellow. You see, it's about defining concepts and relationships logically.
Facts and rules, not just pixel patterns.
Exactly. Now, for a long time, neural networks kind of languished. They hit bottlenecks, the so-called AI winter. But then, like we said, huge data and compute power arrived and they exploded.
Right.
So the core idea, the thesis behind Neuro-Symbolic, is that maybe symbolic AI was also waiting. Not necessarily for the same kind of data or compute, but waiting for neural networks to get really, really good at the perception part, the seeing and hearing.
So neural nets handle the messy real-world input.
Yes. And now that they can do that reliably, we can combine their strength in perception with the strength of symbolic AI in reasoning and knowledge representation.
Marrying the two.
Precisely. Neuro-symbolic computing is about that principled integration, taking the best of both worlds, the robust learning from data of neural nets, and the logical reasoning, the explicit knowledge, the potential for explainability from symbolic AI to create something that's genuinely more powerful and more trustworthy than either approach alone, more than the sum of its parts.
Okay, conceptually, that makes a lot of sense.
Yeah.
But how does it actually work? Can you walk us through an example? How do you physically, or, well, architecturally, combine these two seemingly different ways of thinking about the world? Like, how does the pixel pattern apple meet the rule-based apple?
Great question. Let's use a concrete example, that C-lever dataset I mentioned, the one designed for complex visual reasoning. Remember questions like, are there an equal number of large things and metal spheres?
Yeah, the kind pure deep learning struggles with because it mixes perception and logic.
Exactly. It's hard because the concepts, large, metal, sphere, and the reasoning compare, are all tangled together in one big neural network. Humans don't do it like that, right? We first see the objects, understand the question, and then apply logic step by step.
Makes sense.
So a neurosymbolic system, often called something like a neurosymbolic visual question answering system, mimics that human process. It typically has a few key parts working together. First, you have the vision part, which is usually a neural network like a CNN, but instead of just outputting a single label like objects, it does something more sophisticated. It essentially de-renders the scene. It looks at the pixels and translates them into a structured symbolic representation.
Like a description?
Kind of, but very structured. Think of it like generating a database table or a scene graph on the fly. It would say, Object 1, shape.cube, color.red, size large, material location.xyz. Object 2, shape sphere, colors, blues, size, small, material.metal, location.xyz, and so on for everything it sees.
So the neural network is extracting facts from the image. That's key.
That's absolutely key. It's translating from pixels to symbols. Then second, you have the language part. Another neural network, maybe an LSTM or a transformer, takes the natural language question, like are there an equal number of large things in metal spheres? And it translates that not into an answer, but into a symbolic program.
A program. Like code.
Effectively, yes. A sequence of executable steps based on the question's meaning. So that question might become a little program like scene filter, size large, count, scene filter, material, metal, filter, count two, compare equal, count one, count two. The network learns to convert language into logical operations.
Okay, so you have facts about the scene from the vision net and a program from the language net.
Exactly. And third, you have the reasoning part. This is often a purely symbolic component. It takes the program generated by the language net and simply executes it on the structured scene description provided by the vision net. It runs the steps, filter, count, compare using standard symbolic logic.
And that gives the final answer.
That gives the final answer. But there's a fourth crucial piece. Joint training.
How do they learn together?
This is really clever. The neural parts, the vision net extracting symbols, and the language net generating programs aren't trained separately first. They're trained jointly, often using reinforcement learning. The entire system gets a reward only if the final answer produced by the symbolic reasoner is correct.
Ah, so the reward signal flows back through the whole chain.
Precisely. This forces the neural networks to learn to do their translation jobs well. The vision net learns to extract the right symbols needed for reasoning, and the language net learns to generate the right programs that lead to the correct answer when executed. That symbolic layer, the scene description, and the program acts as a kind of meaningful choke point or interface between perception and reasoning, and that's where it unlocks the benefits.
That architecture is really elegant. It feels like it builds in the logic that was missing before. Okay, so beyond the clever design, what are the actual results? What are the big game-changing benefits that make this approach so promising for building better AI?
The benefits really are quite profound, addressing those core weaknesses we talked about. First off, it solves hard problems that were previously out of reach. On datasets like C-LABAR, these neurosymbolic systems achieve near-perfect accuracy. End-to-end deep learning models just couldn't crack it. Getting that kind of result was a big deal. It earned spotlight presentations at major AI conferences like NeurIPS.
So demonstrably better performance on complex tasks. What else?
Second, and this is maybe the most exciting part for practical applications, massive data efficiency. Remember the small data problem. Deep learning needing millions of examples.
Yeah.
Neurosymbolic systems can achieve better performance than the end-to-end deep learning models using only about 1% of the training data.
1%. Seriously.
Yeah, 1%. And with just 10% of the data, they often reach near perfect accuracy.
That's revolutionary for real-world AI. If you only need 1/100th of the data.
It completely changes the game. Suddenly, AI becomes feasible for all those areas, specialized manufacturing, rare medical conditions, niche financial analysis, where you simply don't have massive labeled data sets. It drastically lowers the barrier to entry and broadens AI's applicability.
Incredible. Okay, data efficiency is huge. What about the black box problem?
That's the third major benefit, explainability and debugging. Because you have that symbolic program as an intermediate step, that filter large count sequence.
Right, the generated code.
You can actually look at it. When the system gives an answer, you can inspect the program it generated and execute it. You can see the logical steps it took. Okay, first it filtered for large objects, then it counted them. Then it filtered for metal spheres, counted those, then it compared the counts.
So you can follow its reasoning.
Exactly. It provides transparency. If it makes a mistake, you can often pinpoint where in the program the logic went wrong, just like debugging traditional software code. This builds trust, makes it easier to deploy, and helps meet those regulatory requirements for explainable AI we talked about.
That's a massive advantage, especially in high-stakes areas. Are there other benefits emerging too?
Yeah, the field is moving fast. We're seeing systems capable of dynamic concept learning. So instead of needing all concepts like red or cube to be perfectly predefined, the neural part can learn to map objects into some kind of internal space, like a color space or shape space, and then learn the meaning of new concepts dynamically from how they're used in questions and answers.
So it could learn what cyan means, even if it wasn't explicitly told beforehand.
Potentially, yes, by seeing it used in context alongside objects it perceives. This is vital because, the world's full of new concepts we need AI to adapt to.
Makes sense.
And taking that even further, there's work on meta-concept learning. These systems try to understand relationships between concepts. For example, learning that kid is basically a synonym for child, or that car and truck both belong to the category vehicle.
So it builds a kind of common sense knowledge structure.
Kind of, yeah. Leveraging these relationships allows for much more flexible and powerful reasoning, making the AI more robust when encountering variations in language or needing to generalize. It's getting closer to how humans use interconnected knowledge.
This visual reasoning example is really compelling, but it feels like just the start. Where else could this neurosymbolic blend be applied? What other horizons are opening up?
Oh, absolutely. It's much broader than just static images. People are already pushing into video reasoning. Think about understanding actions and interactions over time. Projects like Video Sea Lever are looking at relationships between objects and video clips, even exploring counterfactuals. What would have happened if that blue block hadn't been pushed?
Understanding cause and effect in motion.
Exactly. Moving beyond just description to deeper comprehension of dynamic scenes. Another big area is planning. Symbolic AI has always been strong in classical planning problems. Think Tower of Hanoi, solving mazes, scheduling tasks. Neurosymbolic approaches are trying to combine that logical planning capability with the perceptual abilities of neural nets. For instance, instead of planning purely with predefined symbols, maybe you plan within the learned latent space of a neural network that has compressed complex state information. This could open doors for more sophisticated robotics, logistics, or process control.
Interesting. Planning in a learned representation rather than a hand-coded one.
Potentially, yeah. And there's one more crucial horizon we have to mention, which applies to all of AI, but where neurosymbolic might offer some advantages: energy efficiency.
Ah, the power consumption problem. We hear a lot about how much energy these big models
It's
use.
a massive issue. Training some of the largest models can consume electricity equivalent to powering a small city for days. It's unsustainable environmentally and economically if AI is going to scale globally.
How does neurosymbolic help there?
Well, partly through data efficiency, less data often means less training compute needed, but also the research community, including places like MIT and IBM, is attacking this on multiple fronts. They're exploring entirely new types of hardware, things like memristors, analog computing chips, maybe even quantum computing down the line, designed specifically for AI workloads and potentially orders of magnitude more efficient. Plus, new algorithms are being developed alongside these hardware ideas, all aiming to drastically slash AI's energy footprint, maybe by factors of hundreds or thousands. Broad AI needs to be green AI.
That seems absolutely essential for the future. So wrapping this up, it really sounds like neurosymbolic isn't just, gluing two old ideas together. It feels like a genuinely new synthesis, creating something where the strengths of neural nets and symbolic AI actually compensate for each other's weaknesses.
That's exactly the way to think about it. It's synergistic, you get the learning power for perception and the logical structure for reasoning and explanation. And that vision is really what's driving major efforts like the MIT-IBM partnership, that decade-long $250 million collaboration. It's about marrying MIT's deep academic research with IBM's focus on real-world industry problems, using real data and computational scale to push AI towards being broadly applicable, more trustworthy, and yeah, maybe a little more like us in how it understands the world, building on that whole legacy since 1956.
So for you listening, what's the key takeaway from this deep dive into neurosymbolic computing? What does it mean practically, whether you're building AI systems or just trying to understand where this technology is headed?
I think the main thing is that this isn't just theory. It's a practical path towards building AI that overcomes many of the limitations we see today. It points towards AI systems that are fundamentally more trustworthy because their reasoning can be inspected and explained. It enables AI that works with much less data, which is critical for countless real-world applications currently starved for huge data sets. It leads to AI that's more robust and can reason more effectively about novel situations, moving beyond simple pattern matching. For engineers, understanding this architecture, how neural nets translate raw input into symbolic facts, how other nets translate questions into programs, how symbolic engines execute those programs, and how reinforcement learning ties it all together, that's becoming increasingly important. It provides a blueprint for building more capable and reliable AI. It's about making AI genuinely more useful across the board.
It really feels like an evolution, moving AI beyond just being incredibly good at narrow tasks, even if data hungry and opaque, towards something more versatile, more transparent, and maybe, yeah, closer to what we intuitively think of as intelligent. Mhm. So here's a final thought to leave you with. Imagine a future where any significant decision made by an AI, whether it's a medical diagnosis, a financial recommendation, or controlling a complex system, comes with a clear, step-by-step, logical explanation. An explanation that you, not just another AI expert, could actually understand. How might that fundamentally change how we interact with these powerful systems, how much we trust them, and how we ultimately choose to design the intelligent future we're building?